Okay, so let's take a look at some practice problems. So remember, at any point in time, press pause, give it a try, and then watch the video to see how you do, okay? All right, so we've got methanoic acid is the simplest carboxylic acid and is found naturally in the venom of bee and ant stings, which is also called formic acid, from the Latin word for ant, which is formica, which is kind of cool. Okay, so it says calculate the pH, right? Telling us a little story, right? So calculate the pH of, we have a concentration of methanoic acid. So remember, pH means we need the hydronium concentration at equilibrium in order to solve for that. And this 0.50 mole per liter solution is our initial. Okay, so we have here formic acid is HCOOH. We know it's not one of these strong acids, so it must be a weak. So it's going to be HCOO negative 1 plus hydronium, right? And we're going to have to do our ice table. So remember, when you're doing this and everything's kind of mishmashed together, it's not going to say that it's a strong acid or a weak acid. You have to recognize, is it one of the strong acids? And if it's not, then you have to, work it through accordingly. Okay, so here is our initial. Remember, we don't care about water. We start with 0, 0. So we're going to have minus x, 0.50 minus x, plus x, x, plus x, x, right? So now we're going to set up our Ka expression. So essentially, when we want to solve for x to get pH, we have to get x at equilibrium to determine what our pH value is. So we're going to have HCOO negative 1 times hydronium over our original weak acid, right? So the Ka value, you can look this up. So even though they don't tell us the temperature, right, unless they say the temperature, we can assume that it's at 25 degrees. So we would look up this value. So from the appendix at the back of the book, this is 1.8 times 10 to the negative 4 is equal to x, and this guy here is 0.50 minus x. So this is where we want to see, will this 1,000 rule work? Because now we're going to have x squared over an x. So we can't take the square root of both sides, which is what we were used to doing when we originally started doing equilibrium problems. So remember, the 1,000 rule is you take the initial concentration of your weak acid in this case, and you divide it by Ka. So if we were to do this, so this would be 0.5 divided by 1.8 times 10 to the negative 4. This is greater than 1,000, so actually this will work out. So what does that mean? That means that we can get rid of this x, the 0.5 minus x. Remember, you cannot get rid of the x that is not being added or subtracted to something. If you start off with nothing, x is always going to be significant because it's going to make this bigger than 0, okay? But when you have a value that you are either adding or subtracting x by, if x is small enough to not make a huge difference, like if x was 0.00002, if I do 0.5 minus that, I'm going to get 0.4999997 or something. Essentially, it's going to be the same number, right? That's the whole purpose and point of doing that. So we end up getting 1.8 times 10 to the negative 4 is equal to x squared over 0.50, right? So now we can essentially isolate for x. So we're going to do cross multiplication here and then take the square root. So your x value we get is 9.49 times 10 to the negative 3 moles per liter, which is equal to our hydronium, which is the whole purpose of this because they want us to solve for pH. So if we take the negative log of our hydronium concentration, right, we're going to get a value of, now keep in mind, right, for significant digits, so 0.50 is 2, so that means that we're going to have 2 decimal points. Remember, the pH significant digit rules are different. So we get 2.02 for our pH for that solution. Okay, let's take a look at the next one. So we have household vinegar is a simple solution of acetic acid, and the vinegar is titrated to be found to have a concentration of this. Calculate the pH. So literally the exact same thing. Of course, it's just a different acid. So if you'd like, you can give this a try. It's pretty straightforward. Nothing really different about this one here. And then check back in with me. I'm just going to start doing this. You can press pause on the video if you'd like. All right, so we have our equilibrium here, which is going to be now CH3COO plus hydronium, AQ, right? And because this is a weak acid, of course, we know that we are dealing with the ice table here. We don't care about water, so this is minus X, 850 minus X plus X, XX. Right, so our Ka expression is going to be X squared over 0.850 minus X. And the Ka value, which again we can look up at the back of the book, is 1.8 times 10 to the negative 5 for our acetic acid. So if we do the 1,000 rule, I keep saying 100. If we do the 1,000 rule, this will actually work out. So if you do 0.850, so remember when you are doing this, I do want you to prove this, showing me what you are dividing. This is going to be greater than 1,000. So the 1,000 rule will work out. So that's going to end up being X squared over 0.850. So X will end up being 3.91 times 10 to the negative 3. And then, of course, using that to determine the pH, we have 3 decimal places because there's 3 significant digits in the original, right? 0.850. So we end up here with 2.408 for our final pH. So remember, this was our hydronium. Okay, so obviously I'm kind of not showing really all of the steps because it's very similar to that very, very first one we just did. Now, number 3 is a little bit of a different type of problem. It's asking us to solve for the percent ionization, and we have a solution of aspirin that has 0.1 mole per liter. So remember, this is our initial concentration, and they're telling us the pH value of the solution, which is 2.27. Now, percent ionization is essentially the amount of hydronium at equilibrium over the initial concentration times 1,000. So we have to essentially solve for hydronium ions here. So we can do this, and this is at equilibrium because remember, if they give us a pH or pOH value, it is assumed to be at equilibrium. So 10 to the negative pH, or negative 2.27, will give us a hydronium of 5.37 times 10 to the negative 3 moles per liter. And if we plug that in here over the initial, which is 0.10, and of course it's a percentage, we end up with a percent of 5.4% roughly. Now the side to this question was saying, would our simplifying assumption stated above be valid in this case? So what that means is, in this case, would we be able to get rid of our X? Actually you can't. So it is not a valid assumption to get rid of our X, because remember that it has to be less than 5% ionization. So because this is more than 5% ionization, that means our X is going to be significant enough. Okay, so our second set of practice problems is where we are now asked to solve for different things, of course. So you could be asked for, take a look at this, right? So we can be asked to solve for pH, which is what we've already seen. But if you're given pH and you're given the Ka value, you could be asked to calculate the initial concentration of the acid. So kind of working backwards a little bit. So let's take a look at what we are doing here. Okay, so we have citric acid is one of the acids responsible for the sour taste of lemons. what concentration of acetic acid, so we want our initial of our weak acid, would be required to produce a pH of this. Okay, so if you think about it, I'm just going to use HA for short for citric acid. Really, it's just representing a weak acid, just to kind of write down what's going on here. And we'll have citrate and hydronium, right? So usually we have, like the practice problems we just looked at, we were given the initial, but in this case, this is what we're trying to solve for. So we don't care about our water. We start with 0, 0. Now, because they're giving us the pH of 2.5, in other words, what they're telling us is how much product is produced, right? So if I have a pH of 2.50, I can determine what the hydronium concentration is at equilibrium, which is like what we normally call our X value from before, right? So if I do 10 to the negative 2.50, this is going to give me 3.16 times 10 to the negative 3. So that tells me, right, if we were to do this, that this is 3.16 times 10 to the negative 3, and so is this, right? And so really when this is like our original plus x, but it's like plus 3.16 times 10 to the negative 3, right? So here we know that if that's what our, I keep saying x, but it's like what our original x usually is, it's going to be minus that on this side, right? So we know this is going to be x minus 3.16 times 10 to the negative 3, right? So what we can do now is plug these values into our Ka expression. We can look up the Ka for citric acid and determine what this initial concentration would have been. So our Ka is going to be our citrate, right? I'm just simplifying it here, and hydronium over our original citric acid. So citric acid, we can look up the Ka value. It is 7.1 times 10 to the negative 4. This is now 3.16 times 10 to the negative 3 squared over x minus 3.16 times 10 to the negative 3. Right? So now you're going to factor this out and solve for x. Right? So we can cross multiply this here. So we can do 7.1 times 10 to the negative 4 times x minus 3.16. Oops. Times 10 to the negative 3 is equal to, if I were to square that, it ends up being 0.0141. So remember when you're doing this, I know this sounds silly and you're like, oh, miss, I know how to do this. But just as a reminder that when you are multiplying a like something that's a function by a value, you have to apply it to everything that is within that bracket. So it becomes 7.1 times 10 to the negative 4x minus 7.41 times 10 to the negative 4 times this value, okay? So, and then of course you move like, I'm not sure if you need me to show you all of the steps here, but just please, this is the biggest error I see. And then you want to collect like terms on the other side. You should end up here. Please let me know if you have problems with this. We'll go over this again tomorrow. You should end up with an X value of 0.0172 moles per liter, which is equal to our original, remember, our initial acetic acid concentration. And then significant digit-wise, there's 2 decimals, which means we need this only to 2. So this would be 0.017 moles per liter of citric acid. Okay, let's take a look at the next one. Actually, I'm going to probably continue this in part 3 because there's not enough time for this section. See you soon.